Dear students, greetings to you. In this session, you will find the conceptual explanation about multipath fading. I hope you are working on the activities that are posted in the discussion forum as well as the internal assignment questions. Okay, let us start this session that talks about multipath fading in detail. This presentation provides an introduction to multipath fading. We will also be revisiting the classifications of fading. The presentation also provides details about ionospheric and tropospheric fading and concludes with radio wave propagation in the atmosphere. The final slide provides some questions that you have to respond to in the discussion forum. It is important to know when this multipath fading occurs. Multipath fading occurs when signals reach a receiver via many paths and their relative strengths and phases change. In this image, you are seeing a typical multipath propagation. There is a transmitter that is stationed, a receiver that is mobile. You will also see four different paths for propagation. The path labeled A denotes free space which is not distorted. B denotes a reflected signal due to the presence of a building. C denotes a diffracted or diffracted signal. And D shows scattered signal due to the presence of a tree. For you to easily distinguish between reflection and diffraction, please take a look on this image presented here. If you see, reflection involves a change in the direction of waves when they bounce off a barrier. Refraction of waves involves a change in the direction of waves as they pass from one medium to another. And diffraction or diffraction involves a change in direction of waves as they pass through an opening or around a barrier in their path. Multipath fading affects most of the radio communication links in one form or another. Multipath fading occurs in any environment where there is a multipath propagation and the paths change for some reason. This will change not only their relative strengths but also their phases as the path lengths will change. Multipath fading may also cause distortion to the radio signal. As the various paths that can be taken by the signals vary in length, the signal transmitted at a particular instance will arrive at the receiver over a spread of times. This can cause problems with phase distortion and inter-symbol interference when data transmissions are made. As a result, it may be necessary to incorporate features within the radio communications system that enables the effects of these problems to be minimized. Now, I want you to see the image that's presented here. It clearly shows the different bands within the spectrum. Now, multipath fading can affect signals on frequencies from the low frequency portion of the spectrum and below right up to into the microwave portion of the spectrum. Now, in this image that's presented, you are seeing the wavelength range in the spectrum. Low frequency, abbreviated as LF, has radio frequencies in the range of 30 to 300 kHz. Since its wavelengths range from 10 to 1 km respectively, it is also known as the kilometer band or kilometer wave. The microwave spectrum is usually defined as the range of frequencies ranging from 1 GHz to over 100 GHz. Multipath fading is a feature that needs to be taken into account when designing or developing a radio communication system. In any terrestrial radio communication system, The signal will reach the receiver not only via the direct path, but also as a result of reflections from objects such as buildings, hills, ground, water, etc. that are adjacent to the main path. The overall signal at the radio receiver is a summation of the variety of signals being received. As they all have different path lengths, the signals will add and subtract from the total dependent upon their relative phases. At times, there will be changes in the relative path lengths. This could result from either the radio transmitter or receiver moving, or any of the objects that provides a reflective surface moving. This will result in the phases of the signals arriving at the receiver changing, and in turn this will result in the signal strength varying as a result of the different way in which the signals will sum together. It is this that causes the fading that is present on many signals. Multipath fading can affect radio communications channels in two main ways. This can given the way in which the effects of the multipath fading are mitigated. The first one is flat fading. This form of multipath fading affects all the frequencies across a given channel either equally or almost equally. When flat multipath fading is experienced, the signal will just change in amplitude, rising and falling over a period of time or with movement from one position to another. The next one, which is called as the selective fading, occurs when the multipath fading affects different frequencies across the channel to different degrees. It will mean that the phases and amplitudes of the signal will vary across the channel. Mobile phone communications are subject to multipath fading. There are a variety of reasons for this. The first one is considered or will happen when a mobile user is moving. The first is that the mobile station or user is likely to be moving, and as a result, the path lengths of all the signals being received are changing. The second is that many objects around may also be moving. Automobiles and even people will cause reflections that will have a significant effect on the received signal. Accordingly, multipath fading has a major bearing on cellular telecommunications. Now, in the second scenario where other objects are moving, often the multipath fading that affects cellular phones is known as fast fading because it occurs over a relatively short distance. Slow fading occurs as a cell phone moves behind an obstruction and the signal slowly fades out. Now, let us try to appreciate the relationship between wavelength and the wave speed. Now, if you see the presentation slide, we'll be able to understand the calculation of wavelength over a short distance. Now see the problem statement that is presented there. It says the fast signal variations caused by multipath fading can be detected even over a short distance. Assume a frequency of 2 GHz. Example, a typical approximate frequency value for many phones. The wavelength can be calculated as like I had mentioned in the previous slide. In this example, the given frequency is 2 GHz. Now to calculate the wavelength, which is denoted as lambda, we use the formula c/f or c divided by f, where c is the speed of light in meters per second and f is frequency in hertz. If the values are substituted across the correct variables, we get the value of 0.15 meters as wavelength. This example looks at a very simplified version. In reality, the situation is far more complicated with signals being received via many paths. However, it does give an indication of the distances involved to change from an in-phase to an out-of-phase situation. You will be doing some activities pertaining to these calculations and posting the answers in the Blackboard discussion forum once this presentation is over. When a wireless wave is received partly or wholly by way of the ionosphere, it is observed to fade. Much of this fading is due to the interference effects between the waves which have traveled by different paths. Shortwave radio communications is renowned for its fading. Signals that are reflected via the ionosphere vary considerably in signal strength. These variations in strength are primarily caused by multipath fading. Simple diagrams show a single ray or path that the signal takes. In reality, the profile of the electron density of the ionosphere is not smooth, and as a result, any signals entering the ionosphere will be scattered and will take multiple paths to reach a particular receiver. The changes in the ionosphere arise from a number of factors. One is that the levels of ionization vary, although these changes normally occur relatively slowly, but nevertheless have an effect. In addition to this, there are winds or air movements in the ionosphere. As the levels of ionization are not constant, any air movement will cause changes in the profile of the electron density in the ionosphere. In turn, this will affect the path lengths. Many signals using frequency at very high frequency band and above are affected by the troposphere. The signal is refracted as a result of changes in refractive index occurring especially within the first kilometers above the ground. This can cause signals to travel beyond the line of sight. In fact, for broadcast applications, a figure of 4 by 3 of the visual line of sight is used for the radio horizon. However, under some circumstances, relatively abrupt changes in refractive index occurring as a result of weather conditions can cause the distances over which signals travel to be increased. Signals may then be ducted by the ionosphere over distances up to a few hundred kilometers. When signals are ducted in this way, they will be subject to multipath fading. Here, heat rising from the Earth's surface will ensure that the path is always changing and signals will vary in strength. Typically, these changes may be relatively slow, with signals falling and rising in strength over a period of a number of minutes. Multipath radio fading is a factor that appears on most signals to a greater or lesser degree. As radio signals tend to reach a receiver via multiple paths, regardless of how good the path appears to be, there are always likely to be reflections from other objects. The only exception is in outer space, where there are very few significant objects that are likely to cause major issues. In view of the fact that signals take multiple paths and there is always likely to be some movement causing path lengths to change and signal strengths to vary, multipath fading will be an issue in many instances. Radio propagation is the behavior of radio waves as they travel or are propagated from one point to another or into various parts of the atmosphere. The various effects like reflection, refraction, diffraction, etc. all come together in a real way as radio signals propagate through the atmosphere. The signals are affected by a variety of factors, enabling signals to be detected near and far dependent upon a variety of factors. The way that radio signals propagate or travel from a radio transmitter to the radio receiver is of great importance when planning a radio communications network system. In many instances, terrestrial radio propagation is governed to a greater degree by the regions of the atmosphere through which the signals pass. Without the action of the atmosphere, it would not be possible for radio communications signal to travel around the globe on the short wave bands or travel greater than only the line of sight distance higher frequencies. In fact, the way in which the atmosphere affects radio communication is of tremendous importance for anyone associated with radio communications, whether they are for two-way radio communication links, mobile radio communications, radio broadcasting, point-to-point radio communications, or any other radio. The atmosphere can be split up into a variety of different layers according to their properties. Although there is a number of different ways of classifying the different atmospheric regions, typically different scientific displaces may have their own nomenclature as a result of their interest in different properties. The lowest area in the meteorological system is referred to as the troposphere. This extends to altitudes of around 10 km above the Earth's surface. Above this is the stratosphere that extends from the altitudes around 10 to 50 km. Above this, at altitudes between 50 and 80 km, is the mesosphere, and above this is the thermosphere, named because of the dramatic rise in temperatures here. From the viewpoint of radio propagation, there are two main areas of interest. The first one is the troposphere and the second one is the ionosphere. So for troposphere, as a very approximate rule of thumb, this area of the atmosphere tends to affect signals more about 30 MHz or so. The ionosphere is the area that enables signals on the short wave bands to traverse major distances. It crosses over meteorological boundaries and extends from altitudes from around 60 km to 700 km. The region gains its name because the air in this region becomes ionized by radiation primarily from the sun. Free electrons in this region have affect radio signals and may be able to refract them back to Earth dependent upon a variety of factors. The lowest of the layers of the atmosphere is called the troposphere. The troposphere extends from ground level to an altitude of 10 km. It is within the tropospheric region that what we term the weather occurs. Low clouds occur at altitudes of up to 2 km and medium level clouds extend to about 4 km. The highest clouds are found at altitudes up to 10 km, whereas modern jet airliners fly above these altitudes of up to 12 km. Within this region of the atmosphere, there is generally a steady fall in temperature with height. This affects radio propagation because it affects the refractive index of the air. This plays a dominant role in radio signal propagation and the radio communications applications that use tropospheric radio wave propagation. This depends on the temperature, pressure, and humidity. When radio communication signals are affected, this often occurs at altitudes up to 2 km. The ionosphere is the area that is traditionally thought of as providing the means by which long-distance communications can be made. It has a major effect on what are normally thought of as the shortwave bands, providing a means by which signals appear to be reflected back to Earth from layers high above the ground. The ionosphere has a high level of free electrons and ions, and hence the name ionosphere. It is found that the level of electrons sharply increases the altitudes of around 30 km, but it is not until altitudes of around 60 km are reached that the free electrons are sufficiently dense to significantly affect radio signals. The ionization occurs as a result of radiation, mainly from the sun, striking molecules of air with sufficient energy to release electrons and leave positive ions. Much of the ionization is caused by ultraviolet light. As it reaches the higher reaches of the atmosphere, it will be at its strongest, but as it hits molecules in their upper reaches, where the air is very thin, it will ionize much of the gas. In doing this, the intensity of the radiation is reduced. At the lower levels of the ionosphere, the intensity of the ultraviolet light is much reduced and more penetrating radiation including X-rays and cosmic rays gives rise to much of the ionization. As a result of many factors, it is found that the level of free electrons varies over the ionosphere, and there are areas that affect radio signals more than others. These are often referred to as layers, but are possibly more correctly thought of as regions, as they are quite indistinct in many respects. These layers are given designations D, E, F1 and F2. The D region, or the D layer, is the lowest of the regions that affect radio signals. It exists at altitudes between about 60 and 90 km. It is present during the day when radiation is being received from the sun. But because of the density of molecules at this altitude, free electrons and ions quickly recombine after sunset, and there is no radiation to retain the ionization levels. The main effect of the D region is to attenuate signals that pass through it, although the level of weakening decreases with increasing frequency. Accordingly, its effects are very obvious on the medium wave broadcast band. During the day when the D region is present, few signals are heard beyond that provided by ground wave coverage. At night, when the region is not present, signals are reflected from higher layers and signals are heard from much further afield. Above the D region, the next region is the E region, or the E layer. This is present at an altitude of between 100 and 125 km. The main effect of this region is to reflect radio signals, although they still undergo some attenuation. In view of this altitude and the density of the air, electrons and positive ions recombine relatively quickly. This means that after sunset, when the source of radiation is removed, the layer reduces in strength very considerably, although some residual ionization does remain. The F region, or F layer, is higher than both the D and E regions, and it is the most important region for long distance high frequency band communications. During the day, it often splits into two regions known as the F1 and F2 regions, the F1 layer being the lower of the two. At night, these two regions merge as a result of the reduction in level of radiation to give one region called the F region. The altitudes of F regions vary considerably. Time of day, season, and the state of the sun will have major effects on the F region. As a result, any figures for altitude are very variable, and the following figures should only be used as a very rough guide. Typical summer altitudes for the F1 region may be approximately 300 km, with the F2 layer at about 400 km or even higher. Winter figures may see the altitudes reduced to about 200 km and 300 km. Nighttime altitudes may be around 250 to 300 kilometers. Like the D and E regions, the level of ionization for the F region falls at night, but in view of the much lower air density, the ions and the electrons combine much more slowly and the F layer decays much more slowly. As a result, it is able to support radio communications at night, although changes are experienced because of the lessening of the ionization levels. The way in which the various regions or layers in the atmosphere affect radio wave propagation and radio communications is a fascinating study. There are very many factors that influence radio propagation and the resulting radio communications links that can be established. Predicting the ways in which this occurs is complicated and difficult. However, it is possible to gain a good idea of the likely radio communication conditions using some simple indicators. Now, with this, we come to the presentation part. However, you have some activities to accomplish. These are some of the questions that you can answer using the handout and textbook. Alternatively, you can also browse other sources from internet. However, make sure that they are all reliable. Answering these questions will also help you to perform well in the final assessment. The above questions are posted in the discussion forum in your Blackboard page. Here I have presented only 3 questions. However, in the discussion forum, you will find more practice questions. If you like to revisit the presentation video before attempting these questions, please do so. Now, what to submit? Submit the solution document for all the questions with steps involved as an attachment in the forum. Include your full names and student number in the document header. Visit a discussion forum for further details. Thank you for your time, and please note that I have posted the PDF version of this slide in the Blackboard. Have a nice day ahead. Cheers.